Hello, everybody, and thank you for coming to this presentation. So I will present a paper on objective method for stereoscopic 3D quality prediction using visual annoyance and acceptability. So visual discomfort can be introduced at every stage of the broadcast chain, from production to visualization. At the stage of production, geometrical color luminance can be produced to mismatch between two cameras. 2D distortion resulting in view asymmetries can be produced to coding or transmission. Finally, at the stage of visualization, divergence accommodation conflicts can be produced. It's very important to understand that discomfort produced due to view asymmetry or divergence accommodation conflicts is the result of the violation of psychological mechanism of binocular vision. So, for example, in case of severe asymmetries, all viewers will suffer from visual discomfort because brain doesn't manage successfully process discrepancies between left and right views. Hence, we formulate a minimum requirement for any stereoscopic 3D system is to guarantee certain level of visual comfort to all customers. In the context of this study, we want to consider interest of Orange 3D services, because most of the content delivered for broadcasting content view asymmetry that induce visual discomfort. So, for Orange services, it's very important to have complaints of the clients and then improve their service quality. Also, it's motivating to control quality of the produced content for the post-production. So, the first objective was to develop an approach for objective modeling of stereoscopic 3D system quality of experience that allows connecting the technical parameters to 3D viewing experience. And the second is to propose a new objective metric which can guarantee a certain level of visual comfort for customers. Due to sensation of enough depth and eventually occur discomfort, stereoscopic content can be not evaluating using the standard 2D quality concept. Instead, quality of experience is used in recommendation of ITU BT 2021 defines 3 perceptual attributes that collectively affect on quality of experience. They are picture quality, depth quality, and visual comfort. However, to our opinion, depth quality doesn't reflect such artifacts as scoreboard effect and puppet theater effects. So, to consider shape distortion, we are reflect as roundness factor in cinematography. We propose to use 3D geometrical distortion as basic property attribute. This perceptual attribute should be connected with tangible aspect of viewing experience or subjective quality factor. So, in the case of picture quality, we have spatial, temporal, and spatio-temporal distortion. In case of 3D geometrical distortion, can be perceived as magnification, miniaturization in case in planar direction, or compression and stretching in case of cardboard effect. And finally, visual comfort can be experienced as visual annoyance and visual fatigue. Wyckens has demonstrated in his study that visual comfort is the most important axis if there is discomfort. So we think it will be reasonable to focus on this axis when designing objective metric. Also, taking into account the minimum requirement I have talked in the beginning of this presentation is to guarantee visual comfort to consumers. Visual fatigue is a long-term indicator. In this work, it's only used little sequences, so visual fatigue will not be taken account. So, next step in this work is try to link visual annoyance or subjective quality factor to technical parameters, provoking visual discomfort. Here, you have a list of technical parameters considering as evoking visual annoyance in stereoscopic 3D. Then, they should be measured with dedicated algorithms. But the question is, how measured distortion level can be characterized objectively and linked to viewer perceptions. So, it's decided to use a simple ID with 3 colors, which often used in quality monitoring tools. So here, these 3 colors are green, no problem, orange, attention, red, not acceptable, correction is required. This category must be linked to viewer perception, especially to the sensation of visual discomfort. But the question is, what does define boundaries between these categories? So, the first boundary is between annoying and not annoying, and define the annoying threshold. The second boundary is between acceptable and not acceptable, and define acceptability threshold. So, how these categories are linked to technical parameters? In first time, our category are drawn horizontally. Next to it, we'll draw distortion axis of technical quality parameters. So here we can see each category represents a range of distortion level. This range is limited by perceptual threshold, annoyance threshold, and acceptability threshold. By transcending annoyance threshold, change category from green to orange. By transcending acceptability threshold from orange to red. Perceptual threshold represents certain distortion level of technical parameter Px. For example, number of pixels of vertical shift of our rotation degrees. It may be practical to adapt the level of acceptability in the context of marketing or services recruitment. For example, in this case, 80% of acceptability may be a criteria for Orange to decide whether buy or not buy a movie for the broadcasting. By adapting the level of acceptability, we can see we have a distortion range of category red. So, how to define the boundary between objective categories? So, how to define acceptability and annoyance thresholds? For this, we design a subjective color scale which contains same category colors, green, orange, and red, associated with perceptual scales. On these scales, 0.5 corresponds to 50% of acceptability threshold. 1.5 defines 50% of annoyance threshold. Advantages of this scale in comparison with the state of the art that both thresholds are estimated in the same time and direct relation with objective category. So, in the same scale, we have objective prediction that can be evaluated via subjective experiment. After the list of technical parameters was defined, we have to detect them. By the detection, I want to say what we are looking for. For example, in our case, view asymmetry induces visual discomfort. Next, technical parameters should be measured with some dedicated algorithm or software, measured with an algorithm distortion level. Should be compared with correspondent acceptability and annoyance threshold. Thus, perceptual threshold should be defined as a subjective experiment using color scale. Threshold should be defined one for all technical parameters. Then they can be stored in a database. Also, it's preferable that database stores threshold with different acceptability and annoyance level. This allows to adapt objective prediction to different demands, for example, marketing or service requirement. So, when this is accomplished, perceptual threshold can be compared to distortion level. So, when input parameters are ready, 3 messages can be displayed during monitoring. So, the first is no annoying, green. This means that measure distortion level is less than annoyance threshold. Orange, annoying. That means that distortion level is between the 2 perceptual thresholds. And red, unacceptable. This means that measure distortion level is greater than acceptability threshold. To estimate perceptual threshold, we use 3 scenes with different disparity levels. Samvik protocol was used with color scale to evaluate perceptual threshold of 5 view asymmetries: white level, grain level, vertical disparity, rotation, and magnification. So, in this example of result for focal asymmetry, the x-axis represents distortion level. The y-axis represents the mean opinion score collected with color scale for corresponding distortion level. Following the recommendation of ITU BT500, asymmetry logistic function was used to approximate continuous relationship. The perceptual threshold were obtained using this relationship. So, here are resulting thresholds for focal mismatch, and here are the thresholds obtained for all other asymmetries. Their thresholds serve a boundary of objective categories. Next, this plot allows to compare subjective results with objective prediction. So this is the example of result for green asymmetry. X-axis represents distortion level. Y-axis represents mean opinion score obtained with color scale. Subjective categories are defined in accordance with the color scale design. Thus, directly from graph, we can read resulting category from subjective test in the following way. For example, in the test basketball scene, we say this score for different distortion level. Objective prediction can be read following the design of objective categories. So, the boundaries of objective categories are vertical lines representing acceptability and annoyance threshold for green asymmetry, which were calculated as average of 3 cents. So, predict category can be read from the plot like this. So, objective results for basketball scene are here. To investigate performance of the metric, we calculated percent correlation coefficient between subjective votes and objective prediction for all scenes. For green asymmetry, it's pretty 8. Intersection of objective category create color rectangle. When mean opinion score is located outside of triangle, this means that objective prediction has not matched subjective results, like here in this example. There are correlation coefficients calculated between subjective results and objective for 5 views, asymmetry, and 3 scenes. From results, we can see that objective predictions are correlated very well with subjective results with minimum of 0.88 for rotation asymmetry. This reason of flow correlation was that we used two descents. When one of the views was rotated, it created false disparity, which is very easy to notice. Further, we use 50% of threshold of acceptability and annoyance. But how do we evaluate another levels? Due to design of color scale, it can be decomposed in 2 scales. In the first, acceptability scale, the votes can be converted to acceptable and not acceptable. So in red, not acceptable, in green, acceptable. Further, it can be decomposed to annoyance scales. In this case, in red, it's annoying, in green, not annoying. To follow usual shape of logistic function, and it's preferable to invert the data. Basically, such decomposition is data mapping from 1 to 2 datasets. As in previous example, continuous relationship can be approximated from this dataset to evaluation of desired level of perceptual threshold. The question is, how do acceptability and level change with color scale? To estimate this, color scale can be decomposed into annoyance scales and acceptability scales. So, in this case, when you have a score of 1.5 on color scales, it's equal to 49% of annoyance. When you have a score of 0.5 in color scales, it's 55% of acceptability. This result confirmed our initial hypothesis that 50% acceptability and annoyance threshold can be approximated directly from the color scales. Another result is when you have a score of 1 on color scales, 80% experience visual annoyance and 82% accept it. So in our case, acceptability is the acceptance of a certain visual annoyance level. So, the math percentage of annoyance and acceptability can be approximated in two curves. These curves are convenient because the relationship between the color scale and acceptability and annoyance level can be easily found. Using this information, color scale can be adapted to new requirement field. For example, in this case, for 80% of acceptability and 50% of annoyance. This curve can be stored in the system to estimate desired level of acceptability or annoyance and adjust the metrics. But can we use the conventional scales to obtain boundary of objective category for our metric? In order to answer this question, we decide to map threshold obtained with impairment scale and acceptability scale. So, when the score in acceptability scale is 0.8 is equal to 1.6 in color scales. So, using this information to adapt color scale, we can see that orange category disappear. When it's 3.5 on impairment scale, it's equal to 1.2 in color scales. So, in this case, it means that according to our results, annoyance threshold on impairment scale represents not 50%, which one might expect, but 70% of visual annoyance. And to finish, when we have 0.5 on acceptability scale is equal to 3.5 on impairment scales. Annoyance thresholds are equal to 50% of acceptability thresholds, so if these thresholds are used as boundary for our metric orange category, disappear because they are equal. So, to conclusion, in this study, we propose objective metric to predict category associated with viewer perception by using perceptual threshold. For the perceptive is extend propose color metric to another axis of stereoscopic 3D quality of experience or technology. Another perspective is a long duration study to investigate the impact of stereoscopic 3D quality of experience, acceptability or recurrence, duration, and level of view asymmetry. Thank you for your attention, and don't hesitate to ask supplementary questions and information by writing an email to the author, Darya Khaustova and Jérôme Fournier. Thank you for your attention.